Economic and financial variables rarely evolve in isolation. Inflation moves with interest rates, consumption with income, and asset returns across markets. We therefore need models for systems in which several time series interact through time. Our goal is to capture those cross-variable dynamics, estimate them efficiently, and interpret predictive relationships without confusing Granger causality with structural causation. We begin with the vector autoregressive model. A univariate model treats each series separately and can miss useful feedback. Output, inflation, interest rates, exchange rates, and asset prices often respond to their own histories and to one another. A multivariate model can support joint forecasting and describe dynamic interdependence, while causal policy interpretation requires additional identifying assumptions. A vector autoregression, or VAR, generalizes an autoregression to a vector of variables. In a VAR of order P, the current vector y equals a constant vector plus E, coefficient matrices multiplying P lagged y vectors, plus an innovation vector. Every equation may include lags of every variable. The innovation vector has mean 0 and a positive definite covariance matrix called omega. Innovations at different dates are uncorrelated under the basic white noise specification, but components at the same date may be correlated. This contemporaneous covariance is important because it means reduced form forecast errors are not automatically distinct economic shocks. Matrix lag notation lets us compress the whole model. We define an autoregressive polynomial in the lag operator. It starts from the identity matrix, subtracts the first coefficient matrix acting at lag 1, and continues subtracting each later coefficient matrix acting at its own lag, all the way out to lag p. Applying that polynomial to y leaves just the constant plus the innovation. This compact form is what makes deriving stability and impulse responses manageable later on. Any VAR of order P can be rewritten as a first-order system by stacking current y with its previous p-1 values. The enlarged transition matrix is called the companion matrix. Its top row contains the original coefficient matrices, and lower blocks simply move each lagged vector down one position. The companion form turns a high-order model into one first-order recursion. Iterating it separates future innovations from the initial state. Stability requires every eigenvalue of the companion matrix to lie strictly inside the unit circle. Then powers of that matrix vanish, shocks dissipate, and long horizon forecasts return toward the unconditional mean. The same condition can be stated with the determinant of the matrix lag polynomial. Its characteristic roots must lie outside the unit circle. Eigenvalues and polynomial roots are reciprocals under the usual convention, so software output must be read carefully. A root or eigenvalue exactly on the boundary signals non-stationarity rather than ordinary stable dynamics. If an eigenvalue lies outside the unit circle, some component can grow explosively. If it lies on the unit circle, shocks may have permanent effects and cointegration may become relevant. A stable-looking plot is not proof of stability, especially in short samples, so fitted roots should be checked after estimation. Under Gaussian innovations, conditional maximum likelihood has a simple structure. We condition on the first p observations and express each current vector as a multivariate normal variable, whose mean is the fitted VAR and whose covariance is omega. The conditional log likelihood sums these density contributions over the remaining dates. because every equation uses the same lagged regressors, maximizing the Gaussian likelihood for the coefficient matrices coincides with equation by equation ordinary least squares, or OLS. We regress each current variable on a constant and all selected lags. The residual covariance estimate averages the outer products of the fitted innovation vectors. This equivalence makes VAR estimation computationally accessible, but it does not make every coefficient easy to interpret. The number of slope parameters grows with the square of the number of variables and linearly with lag order. A modest system can therefore consume degrees of freedom quickly and produce imprecise estimates. Now, what can we trust about these estimates? If the vector autoregression is stable, the innovations are independent with finite fourth moments, and the regressors are well behaved, then ordinary least squares is consistent. Here is the useful part. If we scale the estimation error by the square root of the sample size, its distribution approaches a multivariate normal one. And the covariance of that limit combines the innovation covariance with the inverse of the second moment matrix of the regressors. So larger samples bias both accuracy and reliable normal approximations. Gaussianity is not required for coefficient consistency or the standard central limit result under the stated innovation and moment conditions. It does simplify the joint distribution of coefficient and covariance estimates. With non-Gaussian or conditionally heteroskedastic innovations, robust covariance formulas may be needed for reliable inference. Lag order is a central modeling choice. Too few lags omit dynamics, leave serial correlation in residuals, and can distort impulse responses. Too many lags introduce many coefficients, inflate estimation variance, and overfit the sample. The preferred order balances dynamic adequacy against the rapid increase in complexity. Information criteria formalize that balance. The AHCAR-EE-CHI criterion applies a relatively light complexity penalty. The Bayesian criterion applies a penalty that grows with the logarithm of sample size. The Hannon-Quinn criterion lies between them. For each criterion, we compare models on the same sample and choose the order with the smallest value. Likelihood ratio tests can compare nested lag orders. The null model restricts all coefficient matrices for the extra lags to 0. Twice the difference between unrestricted and restricted maximized log likelihoods has an approximate chi-squared distribution under regular conditions. The number of restrictions grows with the square of system dimension times the number of omitted lags. Likelihood ratio, score, and Wald tests use different aspects of the same likelihood geometry. The likelihood ratio compares two fitted objective values. The score examines the slope at the restricted estimate. The Wald statistic measures how far the unrestricted estimate lies from the restriction. They are asymptotically equivalent in regular problems, but can differ in finite samples. Residual diagnostics remain essential after order selection. We inspect serial correlation, changing variance, unusual observations, and stability of the fitted roots. A low information criterion cannot rescue a model whose residuals retain systematic dynamics. Nor does a high equation-specific R squared establish a meaningful multivariate specification. Granger causality asks a predictive question. Variable y. Granger causes variable x, if past y, improves forecasts of future x after conditioning on the available history of x and other included variables. The definition compares conditional mean squared forecast errors under a smaller and a richer information set. In a bivariate VAR, y does not Granger cause x when every coefficient on lagged y in the x equation is 0. We test those coefficients jointly, with an F-test, a Wald test, or a likelihood ratio test. Rejection means the lags contain incremental predictive information within the specified system. The result depends on the information set, transformations, lag order, and sample period. An omitted common driver can create apparent predictive direction, while noisy measurement can hide it. A failure to reject is not proof that no predictive contribution exists, especially when the model has low power or the relevant effect is nonlinear. Most importantly, Granger causality is not structural causation. Stock prices may predict future dividends because prices incorporate expectations, even though expected dividends help determine prices economically. A linear transformation or a different set of variables can also alter measured predictive direction. Theory and credible identification are needed for a causal claim. Let me leave you with how this fits together in practice. Start by choosing variables and transformations that make economic sense, then settle on a defensible range of lags. Estimate the stable vector autoregression, look hard at the residuals, and only then test restrictions you have stated clearly in advance. And when you report Granger causality, use the phrase to mean incremental predictability, nothing more. In the next lessons, I will show how impulse responses summarize propagation and how structural restrictions can finally let us reach for causal language. A fitted VAR contains many coefficients, so reading one coefficient at a time rarely reveals the system's dynamic story. Impulse response functions offer a more useful question. If an innovation arrives in one component today, how does each variable respond on impact and at every future horizon? For a stable VAR, invert the autoregressive polynomial to obtain an infinite vector moving average representation, or VMA representation. Current Y equals its mean plus the current innovation and weighted past innovations. The weight at horizon S is a matrix called PSIS, and stability makes these matrices decay over time. The element in row I and column J of PSIS measures the response of variable I, S periods, after a one-unit innovation in component J. For a first-order VAR, PIS is simply the coefficient matrix raised to power S. Higher-order models use an equivalent recursion or companion matrix powers. This derivative is a reduced form impulse response. It describes how an estimated forecast error component propagates through the fitted system. It is useful for predictive dynamics, but it is not automatically the response to an economically isolated shock because reduced form innovations can be correlated at the same date. Standardizing an innovation by its marginal standard deviation makes the size of shocks comparable across variables. It does not remove contemporaneous correlation. If two residual components move together on impact, changing one while holding the other fixed may not correspond to a feasible or economically interpretable event. Let me describe how we build uncorrelated shocks. A common method factors the residual covariance matrix into a lower triangular matrix times its own transpose. If we pre-multiply by the inverse of that factor, we get innovations that are orthogonal and have unit variance. Then the response to the shock in position J is simply the usual response matrix multiplied by column J of that triangular factor. So the factor is what turns correlated forecast errors into separate comparable shocks. This Cholesky construction imposes a recursive contemporaneous ordering. The first variable can affect every later variable immediately, while later variables cannot affect earlier ones within the same period. Reordering the variables changes the factor and can change every orthogonalized response, even though the reduced form VAR is unchanged. Ordering is therefore an identifying assumption, not a cosmetic software option. It should reflect timing, institutional knowledge, or a defensible recursive mechanism. When several orderings are plausible, Sensitivity analysis is more informative than presenting one convenient ordering as fact. Structural VAR methods make these identifying choices explicit. Impulse responses are estimated functions of estimated coefficients and residual covariance. Sampling uncertainty can be substantial, especially at long horizons or near a stability boundary. A point estimate without an interval hides this uncertainty. Pointwise bands answer a different question from a band designed to cover the whole response path jointly. A residual bootstrap provides practical uncertainty bands. Estimate the VAR. Resample-centered residual vectors generate artificial series from the fitted dynamics. Re-estimate the model and recompute the responses. Repeating the cycle creates an empirical distribution at every horizon. The bootstrap must preserve the cross-sectional dependence within each residual vector. Bootstrap bands inherit the fitted model's assumptions. If residual variance changes over time, simple independent resampling may be inappropriate. If the system is unstable or nearly non-stationary, ordinary bootstrap approximations can also be unreliable. The resampling scheme should match the dependence and heteroskedasticity believed to remain in the innovations. A financial case study illustrates the workflow using daily adjusted prices for 4 exchange-traded funds during calendar year 2024. They represent United States large capitalization equities, NASDAQ-oriented growth equities, United States small capitalization equities, and developed markets outside the United States. We first align trading dates and compute log returns as the change in the logarithm of adjusted price. Returns are modeled rather than price levels because the price series are strongly persistent and typically non-stationary. Missing dates and inconsistent adjustment conventions must be handled before any VAR is estimated. Next, we compare candidate lag orders, estimate a VAR with a constant, and verify stability and residual behavior. The chapter implementation uses the AHCAR EEK criterion over a stated maximum lag range. That choice is an empirical rule for this sample, not a universal prescription for all daily return systems. We then compute orthogonalized responses over a 10 trading day horizon. One example traces how a shock associated with the broad market fund propagates to the growth fund. Another reverses the impulse and response variables. These two paths need not be mirror images because the estimated dynamics and recursive identification are directional. The order of the 4 funds matters for Cholesky responses. Placing the broad market first allows its orthogonal shock to affect the other funds immediately. A different order assigns shared same-day movement differently. The labels should therefore describe the imposed shock construction, not suggest that the data alone discovered a unique causal innovation. The response path separates impact, persistence, and feedback. A large impact followed by rapid decay suggests short-lived transmission. A delayed peak suggests propagation through lagged relationships. Alternating signs suggest overshooting or dynamic reversal. Wide bands that include zero warn that an apparent pattern may be sampling variation. Impulse responses can also summarize connectedness. Forecast error variance decompositions ask what share of uncertainty in one variable is associated with shocks in each variable over a chosen horizon. These shares translate response paths into a network-style measure of directional spillovers, but they remain conditional on the model and shock identification. Generalized variance decompositions avoid choosing a recursive order, but their raw row entries need not sum to 1 when shocks are correlated. Row normalization is required before interpreting them as shares. Avoiding Cholesky ordering does not create structural causality. It provides an order invariant predictive decomposition under a different convention. Connectedness depends on horizon. Immediate movement can be strong, while longer-run spillovers are weak, or lagged feedback can build gradually. Reporting one aggregate number can conceal this pattern. We should state the horizon, normalization, variable set, transformation, and sample, because each can materially change the resulting network. Impulse responses can support forecasting interpretation even without structural labels. They reveal how a disturbance in the fitted innovation vector changes conditional forecasts. For policy or causal language, however, we need to explain why the shock corresponds to an external intervention rather than to a mixture of simultaneous news. A common mistake is to interpret every statistically significant response as economically large. Units matter. A one-unit residual shock may be unrealistic across variables with different scales, while a one-standard deviation shock is sample-dependent. Reporting economically meaningful magnitudes and cumulative effects often improves interpretation. Another mistake is to ignore model uncertainty. Changing lag order, sample endpoints, deterministic terms, or variable ordering can reshape a response. Robust analysis compares plausible specifications and benchmarks, VAR responses, with alternatives such as local projections. Stability across choices strengthens the evidence, but never replaces identification. If you remember one thing from this lesson, let it be the line between propagation and identification. The moving average representation tells us how innovations map into future outcomes, and that part comes straight from the estimated dynamics. Orthogonalization then supplies just one possible way to label those innovations as shocks, and bootstrap methods tell us how uncertain the whole picture is. A convincing story keeps these layers apart and says plainly which conclusions come from the data, which from our assumptions, and which are still uncertain. Many macroeconomic and financial level series are non-stationary. Their variances change over time, and shocks can have permanent effects. Modeling such variables in a stationary VAR can produce misleading inference. Cointegration offers a framework for systems whose individual series wander but remain tied by stable long-run relations. A vector random walk equals its previous value plus a new innovation vector. Iterating shows that current y contains the sum of every past innovation. Its conditional mean stays at the initial value, but its conditional covariance grows linearly with time. The process is therefore not covariance stationary. Here is a small mathematical aside, and I want to flag it as exactly that. For a simple symmetric random walk on a lattice, whether it keeps returning to where it started depends on the dimension. In 1 or 2 dimensions, it comes back to the origin over and over, with probability 1. In 3 or more dimensions, it tends to wander off and not return. But this is only an analogy. Cointegration rank is set by common stochastic trends, not by counting how many variables we happen to observe. Cointegration is different from correlation. 2 trending series can have high correlation without any stable relation, while 2 cointegrated series share a long-run equilibrium error that is stationary. Examples include consumption and income, purchasing power, parity variables, money demand systems, and some price pairs in financial markets. Suppose every component of Y is integrated of order 1, meaning its first difference is stationary. The components are co-integrated when a non-zero vector beta produces a stationary linear combination beta prime y. In a 2-variable example, y1 minus b times y2 is the equilibrium error. The co-integrating vector describes long-run relations, but it is not unique in scale. Multiplying beta by any non-zero constant leaves stationarity unchanged. In a rank greater than 1 system, any non-singular rotation of the cointegrating vectors spans the same space. Normalization is needed for numerical reporting and economic interpretation. Rewrite a first-order VAR in differences. The change in y equals a matrix pi times lagged y plus an innovation. When pi has reduced rank r, it can be factored into alpha times beta prime. Beta contains r cointegrating relations, while alpha describes how each variable adjusts to past equilibrium errors. This is the core error correction idea. Short-run changes respond both to recent changes and to deviations from the long-run relation. A negative loading in one equation may pull that variable back after a positive equilibrium error. The sign has meaning only after the cointegrating vector has been normalized clearly. The Granger representation theorem connects 3 views of the same system. A cointegrated process has a vector error correction representation, stationary cointegrating combinations, and a decomposition into common stochastic trends, plus transitory stationary components. With n variables and rank r, the system typically has n minus r common trends. The theorem requires more than a rank statement. Unit roots and stable roots must satisfy appropriate conditions, and the long-run directions must be non-redundant. Its message is conceptual. Permanent shocks move the common trends, while adjustment mechanisms keep selected combinations from drifting without bound. Cointegrating regression can estimate a long-run coefficient unusually quickly. If one integrated variable is regressed on another and their error is stationary, the slope estimator can converge at the sample size rate rather than the usual square root rate. This property is called superconsistency. Superconsistency does not justify ordinary t-tests. The limiting distribution involves functionals of Brownian motion and is generally non-standard. Serial correlation and contemporaneous correlation in the innovations also affect inference. A precisely estimated long-run slope can therefore coexist with invalid conventional standard errors and critical values. Why does Brownian motion keep showing up here? Think of the running total of the innovations. If we scale that total appropriately and let the sample grow, a functional central limit theorem says it approaches a continuous but highly irregular process, and that limit is Brownian motion. The random walk itself is discrete, jumping step by step, while Brownian motion is continuous in time but nowhere smooth. Functionals of Brownian motion give us the right asymptotic language for integrated regressors and for cointegration tests. Without cointegration, regression among unrelated random walks can look highly significant. Persistent stochastic trends generate a high R squared and large conventional T statistics, even when innovations are independent. Deterministic trends can create a similar illusion. This spurious regression problem is why unit root and cointegration analysis must precede long-run interpretation. The Granger procedure provides a 2-step test for one cointegrating relation. First regress one integrated level variable on the others, including the chosen deterministic terms. Then apply an augmented Dickey-Fuller or ADF test to the fitted residual. Stationary residuals support cointegration. The residual test does not use ordinary ADF critical values because the residuals were generated by an estimated first stage. The critical values depend on the number of variables and the deterministic specification. A constant or trend included in the cointegrating regression must be handled consistently in the residual equation. Lagged residual differences are added until remaining serial correlation is adequately controlled. Too few lags distort the test, while too many reduce power. The Granger method is simple, but it depends on which variable is placed on the left, allows only one relation, and separates estimation into two stages. Johann Sen's method treats the whole VAR system jointly. It rewrites a levels VAR as a vector error correction model and studies the rank of the long-run matrix pi. Rank 0 means no cointegration, full rank means the variables are stationary, and an intermediate rank gives that many cointegrating relations. The trace statistic tests whether rank is at most a candidate value against a larger rank. The maximum eigenvalue statistic compares one candidate rank with the next. Both use canonical correlations between residualized changes and residualized lagged levels. Their limiting distributions are non-standard and depend on deterministic terms. Rank selection must therefore be coordinated with lag order, intercepts, trends, seasonal terms, and possible breaks. Trace and maximum eigenvalue tests can disagree. Sequential testing also creates uncertainty that is often hidden when a single rank is reported. Economic interpretability and residual diagnostics should accompany the formal statistics. The chapter case study uses monthly real personal consumption expenditures and real disposable personal income from the Federal Reserve data system, beginning in 1960. We take logarithms, align the series, and inspect their strong upward movement. The unusual divergence around 2020 reflects falling consumption and temporarily elevated disposable income. The unit root evidence is delicate. With linear trends, the reported ADF statistics are -3.74 for log consumption and -3.43 for log disposable income, both close to the 5% critical boundary. First differences reject strongly. The chapter therefore treats the series empirically as I1, while stressing sensitivity to lags, deterministic terms, and sample periods. The residual augmented Dickey-Full statistic is about -3.19. Because the residual-based 5% critical value is near -3.37, the Granger test does not reject the null of no cointegration at 5%, although it does at 10%. Stronger support comes from the Phil-Ips Uli AIR-IS test and Johann Sen's rank tests, which together point to one cointegrating relation. Under a rank 1 vector error correction model, the reported normalization suggests a long-run consumption-income relation with a trend term. The income equation has a significant negative adjustment loading, while the consumption loading is insignificant. In that specification, income appears to adjust, and consumption is weakly exogenous for the long-run parameters. That interpretation is sensitive to normalization and model design. Weak exogeneity here concerns adjustment to the estimated equilibrium error, not general causal independence. Pandemic interventions, measurement revisions, deterministic trends, and structural breaks can all affect the result. A long sample does not guarantee one stable relation across every regime. The practical lesson is to diagnose integration, specify deterministic components, test rank with appropriate critical values, estimate an error correction model, and examine adjustment and short-run dynamics together. Cointegration preserves meaningful long-run information that differencing alone discards, but it must be established rather than assumed from two attractive trending lines. So far we have leaned on vector autoregressions, but they are only one part of the story. In this lesson, I want to widen the lens to vector moving average and vector autoregressive moving average models, which describe how several innovations propagate together. Along the way, we will connect covariance structure, impulse responses, estimation, and approximation. And you will see why the vector autoregression, precisely because it is so easy to estimate, still does most of the work in practice. A stationary VAR captures two kinds of dependence. Coefficient matrices describe dynamic effects from lagged variables across equations. The innovation covariance matrix describes contemporaneous co-movement among unexpected components. Standardizing the variables changes numerical scales, but preserves the underlying system through corresponding transformations of both sets of matrices. For a first-order stable VAR, the unconditional mean equals the inverse of the identity minus the coefficient matrix multiplied by the constant vector. The infinite moving average representation weights past innovations by successive powers of that coefficient matrix. Eigenvalues inside the unit circle make those powers decay. Let me show you how the variance of y is built up. Its contemporaneous covariance matrix solves what we call a discrete Lyapunov equation. Put in words, that covariance equals the coefficient matrix times the same covariance times the transposed coefficient matrix plus the innovation covariance. You can also read it as an infinite sum of past innovation covariances that the dynamics keep propagating forward. The point to take away is simple. Persistence magnifies the variation that comes from contemporaneous shocks. Now, consider covariance across time. At lag k, the autocovariance matrix equals the coefficient matrix raised to the power k times the contemporaneous covariance using the convention of the current vector against its lagged self. The covariance at the negative lag is just the transpose of that. So, unlike the scalar case, these matrices are not generally symmetric at a positive lag. That asymmetry is a feature, not a nuisance. The direction of the cross-covariance carries information that a single autocorrelation number never could. There is a second way to look at the same dependence, organized by frequency rather than by lag. We call it the spectral density matrix. Its diagonal entries tell us how much power sits in each series at a given frequency, while the off-diagonal entries tell us how two series move together at that frequency. The value right at frequency 0 is especially useful. It pins down the long-run covariance of sample averages, and it highlights the slow-moving variation that the series share. Marginal dynamics can be more complicated than the system order suggests. A bivariate first-order VAR typically gives each individual component a univariate ARM, a representation of order 2 and 1, subject to cross-equation restrictions. More generally, a VAR compactly encodes several related marginal models that would look higher order in isolation. A vector moving average, or VMA, of order Q writes Y as its mean, plus the current innovation and Q matrix-weighted, lagged innovations. It is covariance stationary for any finite coefficient matrices when the innovation covariance exists. Invertibility requires the determinant of its moving average polynomial to remain non-zero on and inside the unit circle. Invertibility allows innovations to be recovered from current and past observations through a convergent infinite vector autoregression. It selects a unique fundamental shock representation among observationally equivalent alternatives. As in the univariate case, stationarity of a finite moving average does not by itself guarantee invertibility. For a VMA model of order 1, autocovariance matrices vanish beyond lag 1. The covariance at lag 1 need not equal its transpose and can reveal strong cross-variable transmission. In the chapter's two-dimensional example, a cross-lag correlation can exceed the corresponding own lag correlation, an outcome impossible to understand from separate univariate plots alone. A general vector autoregressive moving average, or VARMA model, combines matrix autoregressive and moving average polynomials. Under stability and invertibility, it has both a convergent infinite VMA representation and a convergent infinite VAR representation. These equivalent forms support forecasting, shock analysis, and approximation. Impulse response matrices are the coefficients of the infinite VMA representation. Their row I, column J element, gives the horizon specific response of variable I to innovation J. For a VAR of order P, the matrices follow a recursion using all coefficient matrices whose lags are available at that horizon. So which shocks should we actually trace? We have a few choices and they answer different questions. Raw responses just use the reduced form innovations. If we standardize each one, the shocks become comparable in size, but can still be correlated. A Cholesky step makes them uncorrelated, but only after we commit to an ordering. Generalized decompositions let us skip that ordering, though we then have to normalize the shares before reading them as forecast error variance proportions. Let me stress the theme. Every convention buys clarity at the price of a different assumption. Connectedness measures summarize how shocks associated with one variable contribute to forecast uncertainty in another over a chosen horizon. They can reveal directional spillovers and network patterns. Raw generalized shares need not add to 1 across a row, so row normalization is necessary before interpreting them as proportions. Multivariate Yule-Walker equations connect VAR coefficient matrices to autocovariance matrices. Replacing population covariances with sample counterparts produces a linear estimation system. The approach is theoretically transparent, but dimensions grow rapidly with the number of variables and lags, making ordinary regression or regularized methods more convenient in larger systems. Equation by equation OLS is consistent when innovations have conditional mean 0 given the past and the VAR is appropriately stable. Because every equation has identical regressors, system generalized least squares gives the same coefficient estimates. Under Gaussian innovations, these estimates also equal conditional maximum likelihood estimates. Model selection combines system likelihood criteria with diagnostics. Equation-specific and system R squared values describe in-sample fit but do not establish a good dynamic specification. We also inspect residual autocorrelation, stability, parameter count, and out-of-sample performance. A high-dimensional VAR can fit extremely well while forecasting poorly. Wald and likelihood ratio tests handle linear restrictions on stacked coefficient matrices, including Granger non-causality restrictions. Under regularity, their null distributions are approximately chi-squared. With martingale difference innovations and time-varying conditional covariance, OLS can remain consistent while the usual covariance formula fails. A robust sandwich covariance uses the variability of score, like products between lagged regressors and current innovations. It accommodates conditional heteroskedasticity under suitable moments and dependence. Robust standard errors do not repair an omitted dynamic variable, wrong lag order, non-stationarity, or an invalid structural interpretation. Impulse responses are nonlinear functions of estimated parameters. The delta method propagates the coefficient covariance through the response recursion to produce approximate normal pointwise intervals. Responses at different horizons are correlated, so simultaneous coverage for an entire path requires wider bands than separate pointwise intervals. Bootstrap methods often provide more flexible response uncertainty. We resample residual vectors or simulate shocks, generate a new series from the fitted model, re-estimate and recompute the response path. The resampling design must preserve relevant contemporaneous covariance and should reflect conditional heteroskedasticity if it is present. Local projections estimate a separate regression at each horizon. With a valid shock measure or instrument and suitable controls, the horizon coefficient estimates a response directly. This approach is flexible and less sensitive to VAR dynamic misspecification, but it can be noisier than a correctly specified VAR, especially at long horizons. Direct VMA and VARMA estimation is harder than VAR estimation. Likelihood surfaces can be non-convex. Matrix polynomial representations may be non-unique, and stability, invertibility, and identification constraints must be enforced. Even the covariance equations of a VMA1 can lead to matrix quadratic equations without a simple closed form. A common practical strategy approximates a stable invertible VARMA process with a higher order VAR. The VAR is easy to estimate and can approximate the infinite autoregressive representation as lag order grows. Lag selection and residual diagnostics remain essential because an unnecessarily long approximation can overfit. The chapter computations connect theory to implementation. They estimate a bivariate macro VAR, compare theoretical and empirical covariances, compute recursive impulse responses and connectedness, simulate a VMA example, and approximate a simulated VARMA11 process with a fourth order VAR. Let me pull this together. The practical advice is to pick your representation to match your purpose. When you want to understand shocks and covariance structure, the moving average and autoregressive moving average forms make that clearest. When you want simple estimation and a flexible approximation, the vector autoregression is hard to beat. Whatever you choose, keep inference honest about parameter uncertainty, changing variance, many horizons at once, and identification. Let convenience guide how you compute, but never let it quietly erase the assumptions behind your interpretation. A reduced form, VAR, describes joint predictability. Its innovations are forecast errors, and their covariance is identified from the data. When those errors are contemporaneously correlated, however, no component has a unique economic label. A structural vector autoregression, or SVAR, adds restrictions intended to identify economically meaningful shocks. The target may be the dynamic response to a monetary policy shock, an aggregate demand shock, or an oil supply shock. Estimating a VAR is not enough to isolate such an event. Identification requires assumptions that map the observed reduced form innovations into mutually distinct structural shocks. In structural form, a non-singular contemporaneous matrix multiplies current Y. Lagged Y terms appear with structural coefficient matrices, and an orthogonal shock vector enters each equation. Pre-multiplying by the inverse contemporaneous matrix produces the reduced form VAR and links reduced form forecast errors to structural shocks. The reduced form identifies the lag coefficient matrices and the covariance matrix omega. It does not identify a unique contemporaneous matrix and structural shock covariance. Many rotations of orthogonal shocks reproduce the same omega and therefore the same likelihood. This observational equivalence is the central structural identification problem. Parameter counting makes the shortage visible. After normalizing structural shocks to have unit variances and zero covariances, a system with n variables still needs n times the quantity n-1 divided by 2 additional independent restrictions. These restrictions must come from timing, theory, sign patterns, long-run effects, external information, or changes in volatility. A common short-run strategy is recursive identification. We impose a triangular contemporaneous structure. The first ordered variable does not react within the period to the others. The second can react to the first but not later variables. Each subsequent variable can react immediately only to variables placed before it. With unit diagonal normalization, the recursive zero restrictions provide the required number of restrictions. Algebraically, this corresponds closely to a Cholesky factorization of the residual covariance. Economically, it asserts a specific within period timing hierarchy. The order must be defended, and alternative plausible orders should be examined. Consider a monetary system containing the price level, real output, money, and a short-term interest rate. One recursive ordering assumes prices do not react within the period to the other variables. Output reacts to prices but not money or rates. Money reacts to prices and output. And the policy rate reacts to all variables. Those restrictions may be plausible with low-frequency data and sluggish price or output measurement, but they are not universal facts. Central banks observe some information in real time. Financial markets react quickly, and aggregation intervals blur timing. Institutional knowledge must explain why the selected zero restrictions are credible for the data frequency. Long-run identification imposes restrictions on the cumulative structural response matrix. The long-run impact is the sum of all horizon response matrices. Setting one element to zero says that a particular shock has no permanent effect on a selected variable, even though short-run effects may be non-zero. The Blanchard-Qua approach separates supply and demand shocks, using the assumption that demand shocks have no long-run effect on the level of output. In a two-variable system, one suitable long-run zero restriction can identify the rotation after standard normalizations. Its credibility rests on the economic model, not on statistical fit alone. Other strategies relax exact short-run or long-run zeros. Sign restrictions require selected responses to have specified signs over chosen horizons. Heteroskedasticity based identification exploits shifts in shock variances. Narrative methods and external instruments use independent historical or high-frequency information correlated with one structural shock. Each strategy has its own failure modes. Sign restrictions can leave a set of admissible models rather than one answer. External instruments must be relevant and exogenous. Volatility regimes must change in informative ways without changing the propagation mechanism. Narrative classifications can be measured with error or chosen after seeing outcomes. The A model places restrictions on a contemporaneous matrix, multiplying reduced form innovations, and assumes a diagonal covariance for structural disturbances. It is natural when equations describe simultaneous relations. Recursive systems are special A models, commonly normalized with ones on the diagonal and zeros chosen by theory. The B model writes reduced form innovations as an impact matrix times unit variance structural shocks. Restrictions are placed directly on that impact matrix. A lower triangular B matrix with positive diagonal gives a Cholesky identification, while other zero patterns can encode a different economic theory of immediate shock transmission. The A-B model is the most general. It lets us restrict both matrices at once. Here, the reduced form innovations equal the inverse of the A matrix, times the B matrix, times the structural shocks. The catch is arithmetic. Two unknown matrices bring in many parameters, so we need correspondingly more restrictions to pin them down. In practice, we often set one of the two matrices to the identity, which quietly collapses the A-B model back into the simpler A model or B model we just met. Regardless of parameterization, the identified impact matrix combines with the reduced form moving average coefficients to produce structural impulse responses. At horizon 0, it maps structural shocks into current variables. At later horizons, the estimated VAR dynamics propagate that impact through the system. Uncertainty comes from both estimation and identification. Conventional bootstrap bands condition on a particular restriction scheme. Comparing alternative credible schemes reveals identification sensitivity that sampling bands do not capture. A narrow band around a response under one fragile ordering can give a false impression of robust causal knowledge. The global oil market example uses oil production growth, a measure of real economic activity and the real price of oil. A structural VAR with 24 monthly lags distinguishes oil supply shocks, aggregate demand shocks, and oil market-specific precautionary demand shocks. Its recursive structure assumes an oil supply shock can affect all three variables immediately. An aggregate demand shock affects real activity and the oil price within the month, but not oil production. An oil-specific demand shock affects only the oil price immediately. Lagged responses then allow broader adjustment over time. The empirical point is that identical oil price movements can have different macroeconomic implications depending on their source. A demand-driven price increase is not the same experiment as a supply disruption. Structural identification aims to separate these mechanisms before impulse responses are given economic names. In R, a practical workflow begins by estimating and diagnosing a reduced form VAR. We then provide a restriction matrix for an A model or B model, leaving selected entries to be estimated. Structural impulse responses follow from the fitted mapping, and bootstrap procedures can quantify sampling uncertainty under that maintained identification. Software can solve the constrained system, but cannot validate the restrictions. We must check order and rank conditions, convergence, admissibility, residual behavior, and whether estimated unrestricted entries make economic sense. Over-identifying restrictions can sometimes be tested, yet failure to reject does not prove the identifying story. Structural and predictive claims should be reported separately. Reduced form results describe forecasting relationships and shock propagation within the statistical model. Structural results add a counterfactual interpretation conditional on explicit restrictions. Calling every orthogonalized residual a policy shock hides the most important assumption in the analysis. Across this chapter, VAR models organize dynamic interactions, cointegration preserves long-run relations, and VARMA representations clarify shock propagation. Structural VAR models bridge these statistical tools with economic theory. Their power comes from making assumptions operational, and their credibility depends on making those assumptions visible, testable where possible, and robustly examined.